Assalamualaikum warahmatullahi wabarakatuh. My name is C51 from Department of Chemistry, Faculty of Applied Sciences in UiTM Marapilis. The title of my paper is Maranta Arundinacea fiber as food packaging material with another authors which is Nurul Nabiha Muhammad Nur Hafizah Uyub, Sarina Muhammad Mutalib Abdullah, and also Nun Daina Masdar. So, what are some of the overview of my slide? There are introduction, methodology, result and discussions, and also conclusions and recommendations. Okay, what is actually arrowroot? Arrowroot, or its scientific name, Maranta Arundinacea sp, and also known as arrowroot. It is a common plant in West Indies, Indonesia, Malaysia, Philippines, and Australia. It also can grow in marginal, dry, and also infertile land under poor lighting condition. Thus, it is suitable for to plant in Malaysia, as Malaysia has tropical weather. So, why is arrowroot special? It is because it has high starch content compared to another plants. According to the table, arrowroot has 35.2% amylose content and also has 64.8 another polysaccharides. And it also has biggest fiber, which is the fiber content in arrowroot is considerably high, which is 28%. It also shorter in length and smaller in diameter compared to sugarcane biggest fiber. And it also can be removed, the non-cellulosic component can be removed by alkali treatment. So, what is starch-based bioplastic? Starch, cellulose, chitosan, and protein are commonly used as renewable and natural resources for synthesizing biodegradable polymers. It also has particularly popular due to their abundance, low cost, and also wide range of application. So, starch has two microstructural types, which is amylose and amylopectin, as shown in the figure above. So, what are the problem segments? First of all, plastic uses and waste. Plastic waste are largely synthetic polymers which are not biodegradable, causing more accumulations of plastic waste to increase daily. Secondly, degradation of synthetic polymer also poses various threats to ecosystem as well as human health. Secondly, limitations of biodegradable plastic. As we all know, starch-based bioplastics are brittle and degrade at high temperature, and their hydrophilic nature leads to moisture sensitivity, which is impacting the tensile strength and water permeability. So, what are the objectives of this paper? Firstly is to extract starch and also its bagasse fiber components from arrowroot using size reduction and alkali treatment. Secondly is to characterize the physiochemical properties of the arrowroot starch and also the composite films. Thirdly is to determine the effect of different fiber loading in terms of tensile strength, biodegradability, solubility, and also water absorption. Okay, firstly we need to extract the starch. The rhizome was sliced into smaller pieces, and the pieces were grinded with 2 to 1 weight over volume ratio with distilled water for 5 minutes. And the pieces will be filtered through double cutter cloth, and starch powder was separated by leaving the solution for sedimentation for 24 hours. So next we need to extract the fiber. The rhizome was sliced horizontally into 7 cm long, and then the pieces were grinded with mortar pestle to obtain the biggest fiber. Thirdly, the extracted fiber were immersed in 3% NaOH solution and stirred for 2 hours at 80 degrees Celsius. And lastly, the fiber were filtered under vacuum via Brashner funnel and dry at 70 degrees Celsius for 6 hours. Okay, first of all, we need to prepare the TPAS or AF composite films. 5 grams of starch were dissolved with distilled water, and different fiber loading, which is 5, 10, 15, and 20%, were added into the starch solution. Next, the mixture were heated until 80 degrees Celsius while magnetically stirred on the hot plates, and 1.5 ml glycerol as plasticizer were added into the mixture and also heated at 80 degrees Celsius for 20 minutes. The solution will let to cool down and pour into 20 cm petri dishes. And last but not least, the films were dried in oven at 45 degrees Celsius for 24 hours. So there are several tests to do to analyze the composite films, which is first of all is optical microscope, second of all digimetric thickness gauge, and third of all Fourier transform infrared spectroscopy. You also need to do a few more tests, which is water content test, water absorption test, film solubility test, and also soil degradability test to analyze the performance of the composite films. We also need to analyze the mechanical properties, which is using the universal instrument 3365. So, these are several of result and discussion that we have did. First of all is FTIR analysis. From the spectra, we can identify several important peak, which is hydroxy, CH stretching, which is indicate the glucose unit, and also the COC stretching, which is indicate the glucosidic bonds among the starch granules. So, this is the FTIR analysis for the TPAS AF composite films. There are 5 composite films that has been prepared. First of all is control, 5%, 10%, 50%, and 20%. According to spectra, there are several important functional groups that can be identified, which is the hydroxyl, CH stretching, carbonyl, CO, which is the glucose pyranose, and also the anhydrous glucose ring. So, next test is thickness and also the moisture content. The thickness of composite film increased with the addition of fiber. The thickness for TPAS, the AF 10% was lower than 50% due to the content of dry mass per unit area of the film forming solution. And also increasing the fiber amount can lead to higher amount of solid in the solution. Therefore, it also contains small amount of lignin, which can contribute to the increasing thickness of composite films. And also, the moisture content will increase due to the porosity of the composite films. So, this is the result of the optical microscope test. There are several fiber that can be observed throughout the composite films when the fiber is added into the films. Composite film at 20% fiber loading exhibited the lowest solubility compared to other films. It was caused by the hydrogen bond formation between starch chains and also hydroxy groups in fiber. It will increase the water resistance and stability of the composite films. Next test is soil biodegradability test. 20% fiber loading took 40 days to decompose completely. Meanwhile, 15% fiber loading took 15 days to fully decompose, and also the addition of fiber improved the degradation rate of the composite films. It is due to the high water content in the composite films, and it also more suitable for bacterial attack, which cause the decomposition. The composite films with fiber loading had lower water absorption compared to the control films. It is because the fiber helps to protect the polymer matrix when exposed to extremely humid conditions. And also it reduces the hydrophilicity of the composite films, and the alkali treatment roughens the fiber's surface, improving the adhesion between the fiber and also the matrix. 15% fiber loading composite film had the highest tensile strength at 2.2 megapascal. The tensile strength was increased along the addition of fiber loading until 50%. It is caused by strong interaction between the starch and fiber molecule, and the tensile strength for 20% fiber loading was reduced due to poor dispersion and fiber distribution within the polymer matrix. 50% fiber loading film show the highest Young modulus, which is at 27.08 megapascal. It shows the same trend as tensile strength of the composite films. It is caused by the high compatibility between the starch and fiber, and the addition of fiber as fillers, creating stiffer polymer matrix. Last but not least, elongation at break. Elongation at break of the composite film was decreased along the addition of fiber. It is because the composite film becomes stiffer after adding the fiber. And last but not least, the increased thickness caused stiffer polymer, which is caused the composite film because less stretchable. As conclusion, increased fiber loading resulted in thicker films, higher water content, and also better biodegradability. And decreased solubility and water absorption are beneficial for food packaging. And tensile strength improved with fiber addition. Elongation at break decreased due to the increased stiffness, and the optimal fiber loading was 50%. There are 2 recommendations that we can do to improve the analysis, which is TGA, thermogravimetry analysis, and also SEM, which is scanning electron microscopy.